Okay, we're now making a video going over Unit 5 notes for Unit 5. This is the periodic law. We're going to take a look at pages 1 and 2 here. So we're going to start off by going over sort of a brief history of the periodic table and how it was developed, and then we'll get into some of the finer aspects of the periodic table. So history of the periodic table starts with a scientist or chemist by the name of Dmitry Mendeleev. So one thing we need to start with is by discussing the fact that elements can be arranged according to their physical and chemical properties. And for many years, chemists were trying to arrange elements into some sort of classification system based on their physical and chemical properties, and they were not successful at doing this until Mendeleev comes along in 1869. He's a Russian chemist, Dmitry Mendeleev, and he made the first truly accurate and useful periodic table, and he did so by arranging elements in order of increasing atomic mass. And over here on the right side, right over here, you can see a reproduction of Mendeleev's first periodic table, which, as it says, was arranged into vertical periods, not horizontal periods like we have today, according to relative atomic mass. That's Mendeleev's first periodic table, the first functional, useful periodic table. Now, this periodic table was very useful at the time, and was the best we could do at the time, because we did not have a way of measuring protons. In fact, protons had not yet even been discovered. It was not for another 30 or 40 years that protons were actually discovered. Once protons were discovered, though, about 40 years later, an English chemist by the name of Henry Moseley was looking at Mendeleev's table, and there's some inconsistencies in Mendeleev's table. In some cases, it seemed that atoms, or elements, I should say, were out of order, that they were not in the order that you would expect if they were arranged by average atomic mass. So he made a new periodic table that was arranged by increasing atomic number, and everything fell into place, and the modern periodic table was born. It turns out that this was actually the key to finding a periodic table, the current periodic table that we have, that is useful for us. Now, as we move forward, this chapter has a lot of content to learn. It's not a lot of math like some of the previous chapters we've had, but there's a lot of things to kind of learn and understand, concepts and ideas, and some of that includes vocabulary. So one of the first vocabulary term we have here is periodic law. So periodic law states that the physical and chemical properties, of the elements are periodic functions of their atomic numbers. Now, periodic function means that they are repeating. So physical and chemical properties repeat in relationship to atomic numbers. As atomic numbers increase, eventually you have these chemical and physical properties that recur periodically, and they recur at sort of a regular, predictable way. So put this in a different way. When elements are arranged according to their atomic numbers, elements with similar properties will appear at regular intervals. So if we arrange the elements in order of their atomic number, we begin to see a pattern emerge where elements with similar properties will begin to appear at regular, predictable intervals. And that is actually how our modern day periodic table is constructed. So let's take a look at the modern periodic table. Let's start talking about it. So the periodic table has undergone extensive change since Mendeleev's time. We've added more than 40 new elements to the periodic table since that time. Now, in Mendeleev's, one really neat thing that Mendeleev was actually able to do with his simple periodic table based on atomic masses was he actually was able to predict the existence of elements. If you look here on his periodic table, you see there's at least 3 elements here or 3 spaces here where there are question marks. And these were places where Mendeleev predicted there must be some element that exists to fill this space, but it had not yet been discovered. And he actually was able to predict some of the properties of those elements, such as their general appearance, their density, their melting points, these sorts of things. And he was able to very accurately predict some of these things. And these 3 spaces now we know are the elements scandium, gallium, and germanium, for example. So Mendeleev was definitely onto something here, but it wasn't, because he didn't know about protons and we didn't have atomic number at his time, he wasn't able to go all the way to a complete periodic table, but now we know. And so we've added about 40 new elements. All of these additions, however, can be placed in a group of other elements with similar properties. So we've added elements to it, but after Moseley, basically we've just sort of been adding to his periodic table. Not a lot of changes to the basic order have taken place since then. So we have some additional vocabulary here. Like I said, this is a content-heavy unit. There's a lot of vocab terms and there's a lot of new concepts to learn, not a lot of math. Maybe for some of you that's a relief. For some of you, you may like the math. But in any event, we'll take a look at some new vocab terms here. Actually, group and period should not be new. But the periodic table is an arrangement of the elements in order of their atomic number, so in order of their atomic numbers, such that elements with similar properties fall in the same column or group. So elements with similar properties fall into the same column or group. So what is a group? Just this is a review vocab term. We've already learned these. Groups are the vertical columns of elements in the periodic table, and elements in the same group, we should note, and it is important that you remember this, will have similar chemical properties and actually similar physical properties as well. And then we have periods. So the periodic table is arranged into rows and columns. The columns are the groups and the rows are the periods. So periods are horizontal rows of elements in the periodic table, and elements that are in the same period will have the same number of occupied principal energy levels. So what this is saying is that if you have elements that are in the same period or the same horizontal row, they will have electrons in the same number of energy levels. And the number of energy levels that they will have is equal to the period number. Okay? So the highest occupied principal energy level is equal to the period the element is in. Okay? So you look at any period or row on the periodic table, the element that's in any element in that row, the highest energy level that it will have electrons in is equal to the period number. All right. So now there is a connection between, and we talked about this a little bit in the last unit, but there's a connection between electron configuration and the periodic table. So in general, the electron configuration of an atom's highest occupied energy level governs the atom's chemical properties. So this is something that's important to understand. Chemical properties or chemical reactivity is directly related to the electron configuration of an atom, specifically what electrons does it have in the highest occupied energy level. So chemical reactivity is related to the electrons that an atom has in its highest energy levels. Let me repeat that. Chemical reactivity is related to the electrons that an atom has in its highest occupied energy levels. Okay, so the periods of the periodic table are determined by electron configuration. So based on electron configurations of the elements, the periodic table can be divided into 4 blocks. So if we look at electron configurations, which is what the last unit was all about, we did lots of electron configurations. The periodic table actually mirrors electron configurations, and if you understand the way the periodic table is arranged, it helps you with electron configurations greatly. So there are 4 blocks. The periodic table can be divided into 4 blocks. The first are the S block, the second is the P block, the third is the D block, and the fourth is the F block. And right down here we see a periodic table that has been divided as such. So over here on the left side we see that these are the S blocks. Right here, those are the S block elements. There's the groups 1 and 2. The P block elements are over here. Those are groups 13 through 18. Those are the P block. The D blocks are right here. Those are the D block elements, the transition metals. And then down here are the F block elements, also called the lanthanides and actinides. All right, so the periodic table is divided up into these different blocks if we're looking at electron configurations. Now what this tells you is basically, this is the gist of what this tells you in relation to electron configurations. Any element that is in group 1 right here or group 2 is going to end, its electron configuration will end in S. If they're in group 1, it's going to end in S1. If it's in group 2, it's going to end in S2. And that's it. Its electron configuration will end in S1 or S2. Those are the S block elements. The P block elements are the groups 13 through 18, that's 6 groups, and they will end in P1, P1, P2, P3, P4, P5, or P6 respectively, depending on which of these 6 groups they are in. The D block elements likewise give elements whose electron configurations will end with D. Now, the D block electron configurations are always one behind the period that you're in. So if you're in period 4, you go 4s1, 4s2, and then you go down to 3d. So it's the period that you're in minus 1 and then d. And then the F blocks are minus 2. So it's a period you're in minus 2. Actually, I think that this is an error. That should say 4 and 5. Those are errors right there, actually. It should be 4 and 5. Make sure you make that correction. Okay, so it's anything in this first row of the lanthanides and actinides, that's 4F, and down here, anything in this row is going to end in 5F. All right. Now, that's one way that we can look at the periodic table as it's broken down into different blocks relating to electron configuration. Now, we're also going to take a look at some other ways of grouping or looking at elements within the periodic table. And the first thing we'll take a look at are the main group elements. So main group elements are elements that are in groups 1, 2, and 13 through 18 of the periodic table. So main group elements are in the S and P blocks, in other words. So let me scroll back up here just a little bit. So you see the S block, it's groups 1 and 2, and the P block is groups 13, it's 13 through 18. And so those are main group elements. Now, what's special about the main group elements, what's very helpful about the main group elements, is that main group elements have regular and consistent electron configurations. It's very easy to predict the electron configurations because there's no irregularities. The D block and the F block elements do have some irregularities, and in first year chemistry it's not that important for us to get into those irregularities, but you should know at least that there is some irregularity there, but I'm not going to hold you to knowing it this year. So main group elements that are in the same group all have the same number of valence electrons. So here's a term we may have already talked about a little bit this year, may have heard it before, but valence electrons are electrons that are found in the outermost energy level, or the highest energy level of an atom. So valence electrons are those electrons that are in the very highest energy level of an atom. So elements in groups 1 and 2 have the same number of valence electrons as their group number. So this is a little shortcut right here. I've got stars here for a reason. This should help you remember it. Because knowing the number of valence electrons actually helps you make some predictions about chemical reactivity as we move forward in this class. So electrons in groups 1 and 2 have the same number of valence electrons as their group number. So for example, beryllium, magnesium, calcium, strontium, barium, and radium are all in group 2. Those are all in group 2. And so the shortcut says that they all have 2 valence electrons. Okay, so if I were to ask you how many valence electrons do elements have in group 2, or do the elements in group 2 have, and the answer is very easy because they're main group elements, and it's just equal to the group number. Now another shortcut, elements that are in groups 13 through 18 have their group number minus 10 valence electrons. So for example, carbon, silicon, germanium, tin, carbon, silicon, germanium, tin, lead, and ununquium, I think is what that is. You don't have to worry about that one probably ever. But they're all in group 14. So if we look at this little shortcut right here that says elements in group 13 through 18 have their group number minus 10 valence electrons, you should be able to figure out how many valence electrons carbon has, and silicon and germanium, and so on and so forth. It's the group number, which is 14 minus 10. So they all have 4 valence electrons. This will become important as we move forward later. It's very, very simple and easy to figure out with the main group elements, those elements that are in groups 1 and 2 and 13 through 18. So just these are little shortcuts here to figure out the number of valence electrons. It's just something to hold on to as we move forward in this course. All right, that's it for pages 1 and 2 of our notes. There'll be another video for pages 3 and 4 coming shortly.